Hi, my name is Talia, and I'm an incoming high school senior who's super passionate about teaching others chemistry and math. I started this YouTube channel as a supplemental resource to help people who may be having difficulty in their chemistry classes. Last week, I talked about Bohr diagrams and ions, and today I'm going to be talking about light. So if you need help with light and light calculations, feel free to continue watching. And without further ado, let's get started. Okay, so I'm going to define light in two different ways. Light can be defined as both a wave and a particle. So first, light is a wave, which means it is part of the electromagnetic spectrum, which just represents all the different waves in the world. And all of these different waves give off radiation. And these waves all also have a wavelength and a frequency. And a wavelength is the distance between the peaks of a wave. So as you can see here in this example, this is the wavelength, as I showed. And then there's also a frequency, which is how many waves pass a given point in a second. And wavelength is measured in meters because it is the distance between the peaks of a wave, and frequency is measured in hertz. And 1 hertz is equal to 1 over a second. So wavelengths and frequencies are inversely related. When a wave has a shorter wavelength, it has a higher frequency because if you think about it, the waves are more compressed, so more waves are going to pass a single point in a second. When there's a longer wavelength, less waves will pass a point in a given second, which means there will be a lower frequency. And you can calculate wavelength and frequency using the equation C equals lambda nu. And the first variable after C is a lambda, and the second one is a nu. Those are Greek letters. So C represents the speed of light, which is 3.00 times 10 to the 8 meters per second. Lambda represents wavelength, and nu represents frequency. Remember, wavelength is in meters and frequency is in hertz. Okay, so we are going to do the first problem. We have an X-ray with a wavelength of 1.50 times 10 to the negative 9th meters, and we are being asked to find the frequency. So I'm going to write out the equation, C equals lambda nu, and plug in what we know. So we have 3.00 times 10 to the 8th meters per second for speed of light equals lambda, which is the wavelength, times nu, which is the frequency. Now we are going to divide both sides by 1.50 times 10 to the 9th meters and plug that into your calculator. We get that the frequency equals 2.00 times 10 to the 17th hertz. Now the units, the way that that cancels out, we have meters per second, and we are dividing it by meters, but when you divide a fraction, you multiply by its reciprocal. So we are going to multiply by 1 over meters, and the meters cancel out, and we get 1 over second, which equals hertz. Let's do our next problem. A microwave has a frequency of 4.0 times 10 to the 10 hertz. What is the wavelength? Same equations. C equals lambda nu. I always like to write it out first. So we have 3.00 times 10 to the 8 meters per second equals wavelength times 4.0 times 10 to the 10th hertz. And then you will divide both sides. These numbers cancel out. And then we divide 3 times 10 to the 8th divided by 4 times 10 to the 10th. We get 0.0075 meters for the wavelength. Let me show you how these units cancel out. So we had 3.00 times 10 to the 8th meters per second, and we know that hertz is 1 over second. So we're dividing by 4 times 10 to the 10th hertz, which means we're multiplying by 1 over 4 times 10 to the 10th hertz. But if we rewrite it like that, because this is a 1 over here, over seconds, we can rewrite this fraction as times a second up here and 4.0 times 10 to the 10th here. So now these seconds cancel out and we are left with meters. Okay, so for our last example, we have 91.5 megahertz as the frequency. We're finding the wavelength. Our first step is we need to convert to hertz. So we have, let me zoom in, 91.5 megahertz times, and then if you look at your metric conversion chart, 1 times 10 to the 6th hertz is equal to 1 megahertz. So if we multiply 91.5 times 1 times 10 to the 6th, we get, so we have 9.15 times 10 to the 7th hertz, and then now we can plug that into our C equals lambda nu equation. So we have 3.00 times 10 to the 8th meters per second equals lambda, and then 9.15 times 10 to the 7th hertz. Divide both sides by 9.15 times 10 to the 7th hertz. I've already showed you how the units work out. We get 3.28 meters as the wavelength because of rounding. Okay, so that's light as a wave. It has a wavelength and a frequency, and it's part of the electromagnetic spectrum. Now we're going to talk about light as a particle, which basically means that light has energy. So it was concluded by Max Planck that the energy of electromagnetic radiation depends on its wavelength and frequency. So that in part with Albert Einstein's conclusion that light is made up of photons, which is basically a stream of particles, led to determining that light has energy. Albert Einstein concluded that depending on a kind of radiation's wavelength and frequency, or the energy of the photons can change. So each photon has a specific amount of energy. This is supposed to say photon. Okay, so the photoelectric effect was carried out to prove this point, and this basically shows that when light was shined on the surface of a metal, electrons were bounced off. And in order for the electrons to be emitted, the light needed to have enough energy to hit the metal and have electrons bounce off. So the more energy a kind of radiation has, the shorter wavelength it has and the high enough frequency it has. Because if you think about it, a high frequency means there's more of the radiation because more waves are passing in a second, which means there's more energy. So every kind of metal required a specific amount of energy to emit electrons, but this basically showed that with a high enough frequency and the correct metal, light can demonstrate the fact that it has energy and electrons can be emitted off of a metal. So all of those words can be shown in the equations that can be used to determine the energy of electromagnetic radiation in these equations. So E equals h nu, or E equals hc over lambda. E is energy, which is written in joules. H is Planck's constant. C is the constant we already learned, the speed of light. You already know lambda is wavelength, and frequency is represented as nu. Okay, so let's try our first problem. A microwave has a wavelength of 0.0245 meters. What is the energy and what is the frequency? Okay, so we are going to start with our first problem, which says the microwave has a wavelength of 0.0245 meters. What is the energy and what is the frequency? So the best thing to do, because you have an additional variable, is to determine which variables you already have numbers for. So we have wavelength, and we're looking for energy and frequency. So which equation can I use? I can't use E equals h nu because we don't have nu. So I have to use E equals hc over lambda. So let's write that out. So I'm going to plug in what I know. First, I have Planck's constant, 6.626 times 10 to the negative 34th joules second, times the speed of light, all over the wavelength of 0.0245 meters. And then that gets us 8.11 times 10 to the negative 24. And our unit is joules. And remember, in your calculator, this multiplication should occur first, so make sure you are doing that properly with parentheses. So there's our energy, and I'll show you how these units work out. For the Planck's constant, we have joules second, and we are multiplying that by meters per second, so the seconds cancel out. And then we multiply joule meters by 1 over meters, and we just get joules, which is the same as this. Now let's figure out the frequency. So we're going to use E equals h nu because that has the energy, the Planck's constant, and the frequency, which is what we're looking to find. So we have our energy. Make sure you keep the unrounded version in your calculator. And then let's plug in our constant. And then divide both sides by the constant. And then what you can do in your calculator, keep the unrounded version in and just hit the divide button and divide by the constant. And we get 1.22 times 10 to the 10th hertz. Beautiful, so we solved this problem. So next we're going to talk about the atomic spectrum, and spectrum represents the light that is given off by an atom. So when you apply electricity to an atom, it can jump to an excited state, which basically means that an electron can jump to a new orbital. And we talked about in the previous video how Bohr diagrams represent the the shells outside of the nucleus. So in an excited state, an electron can jump from, let's say, the second orbital to the fourth. And so it jumps to that state, and when it returns back to the ground state after the electricity is hit to it, light is given off by the atom. And the prism can separate the lines, the different lights that are given off in the stream of light that is given off by the atom. Like, it can separate it into different colors, and an emission spectrum can be produced. So the differences in spacing between the orbitals of the atom, like between the first and the second, third, and fourth, that can be represented by different wavelengths in the emission spectrum. Okay, so we're going to practice an example of this, and it basically is just all we've learned in this video so far combined into one part. So in a hydrogen atom, the light emitted when an electron falls from the fourth energy level to the second energy level is 486 nanometers. And the light emitted when an electron falls from the fifth energy level to the second energy level is 434 nanometers. So let's dissect that question, or that background information. Electricity was applied to a hydrogen atom, and one electron jumped to the fourth energy level, and another jump to the fifth energy level. Now, both of those electrons have come back down to their regular orbitals, and light has been emitted. And the wavelengths of each of those distances have been measured, and as you can see, the colors and wavelengths produced, that represents the differences in spacing between each orbital. So we have a differencing in spacing between the fourth and the second, and the fifth and the second. So this has multiple parts, and you're going to try this on your own. You have to determine the frequency of these wavelengths, the energy of these wavelengths, use this diagram to show the transitions taking place, like show lines between the orbitals, and use the information you already have to determine what energy level would be emitted when an electron falls from the fifth energy level to the fourth energy level. Okay, so the final part of this problem is to figure out what is the frequency and wavelength of the light emitted when an electron falls from the fifth energy level to the fourth energy level, and does the radiation fall into the visible range of 380 nanometers and between 380 nanometers and 740 nanometers. And as you can see, that is in nanometers. So give this a shot on your own, pause the video, and when you're ready, we're going to go over the solutions. Okay, so here are the solutions. I'm going to do each part individually. Determine the frequency of these wavelengths. This is using the light as a wave equations. So I wrote out the equations here, And then because we're solving for frequency, I solved for frequency in the equation just to make things a little easier for myself. If you want, you can write it out fully and divide both sides. I did the same thing, just skipped a step. So I first converted the nanometers into meters because you need to do that for the equation because wavelength needs to be in meters. Then I solved in both cases to get the frequency, which is 6.17 times 10 to the 14th hertz from the fourth to second energy level, and 6.91 times 10 to the 14th hertz from the fifth to second. So next, we need to determine the energy of these wavelengths, which you can do using E equals h nu. You can also do this using E equals hc over lambda. This is what I chose to do. You'll get the same answer either way. And these are the energies I got. 4.09 times 10 to the negative 19th joules corresponds to the fourth to second energy level. 4.58 times 10 to the negative 19th corresponds to the fifth to second energy level. Part C, I copied down my diagram, and as you can see, I just illustrated everything. From the fifth to second energy level, it took 4.58 times 10 to the negative 19 joules for the electron to jump back down. Here's the energy from the fourth to the second, 4.09 times 10 to the negative 19 joules. You will see in the next problem that if you just subtract the two energies, you will get the energy required from the fifth to the fourth energy level. So let's do that. I subtracted 4.58 times 10 to the negative 19th minus 4.09 times 10 to the negative 19th, both of those are joules, to get 4.90 times 10 to the negative 20th joules. So we're trying to get energy from the energy required from the fifth orbital to the fourth. So I subtracted the fifth to the second minus the fourth to the second, and all we have left is the fifth to the fourth. And that you can see in this equation as well. All of this was subtracted away, and we're just left with this. Now let's find the frequency and wavelength of light emitted when the electron falls from the fifth energy level to the fourth energy level. Reminder, we're trying to get in this range. Okay, so our first step is to determine the frequency. That's just what I chose to do first. So I wrote the energy that I got from this problem, making sure to keep all the unrounded versions in my calculator for this whole problem, dividing both sides by 6.626 times 10 to the negative 34th joules seconds to get the frequency, 7.40 times 10 to the 13th hertz. So now we want to get the wavelength, and we can just plug that in using C equals lambda nu. You could have also used E equals hc over lambda. There are multiple ways to go about this. But again, as I wrote here, keep the unrounded version for the frequency in your calculator. So I just plugged everything I knew in, divided both sides by the frequency to get 4.06 times 10 to the negative 6 meters. Now we've solved this part and this part of the problem. Next, we want to see, will it be in the visible range of light? So to do that, because the units for the visible range are in nanometers, we need to convert to nanometers. So I converted, did a basic metric conversion to get 4.06 times 10 to the third nanometers. And that is not in this range. Therefore, it does not fall in the visible range of light. And that is this final problem. I hope you enjoyed this video on light. Next week, I'm going to be talking about basic quantum mechanics. So orbital notation, electron configuration notation, noble gas notation. So if you need help with those topics, feel free to watch my next video. If you have any questions, you can leave them in the comments and I will try my best to answer them. I will also be leaving a link in the description of my website where you can register for tutoring and watch all my YouTube videos. I hope you enjoyed the video and good luck with learning your chemistry.